Okay, so the code basically does is, like OCR 0, OCR 0 is 50. So when it goes to 50 clock cycles, it will go like that, 50 microsecond cycles. T flag initially at 1. So when the interrupt service happens, or when the timer reaches to 50, so interrupt is generated and comes to here. T flag is 1. T flag is like an arbitrary variable, right? And then I change this OCRO value to 150. So on the new value written to this OCRO is 150. So so this pin is set to toggle, no? Right? So it will toggle to high and wait for another 150 microseconds. Because OCRO is now 150. You can't use any value more than 255. That is the maximum value. Then again, now same time I have to set the T flag to 0. So in the next time when the interrupt is generated at 150, so T flag is now 0. So it will check this one because now it is false. It has to come here and set this OCRA or new value to 50. So by the same time, it will toggle the output pin to this to low and wait another 50 microseconds. Likewise, this cycle will be repeated, right? So I have to make a correction. So this problem should be 50 microseconds off and 150 microseconds on, right? And so that is happening on OCOA output pin. Likewise, you can use this code. You can generate any arbitrary waveform with different duty ratio by adjusting these two values. Okay. Now the second option is the third option of generating PWM signals is to use fast PWM mode. So here the frequency of the PWM signal is you can have different duty ratios, right? So the frequency of your square wave is like this is your on time, right? And this is your off time. And this is your periodic time, right? So the periodic time is this one. So the frequency is 1/T. And so that is given by this CPU clock frequency divided by the free scalar divided by 256. 256 is the maximum value. 255 is the maximum value that you can have, but it can go up to 1 when it generates the interrupt. That's why this number came. So all you need to do is know is the maximum frequencies given in this equation. That is the CPU clock frequency divided by pre-scalar divided by 255. So if you take the 1/that, that is the time period of your square wave signal. And T on period and T off period can be adjusted by software. Yeah, I will explain it how to do it. So by using this kind of PWM signal, you can change the speed of a motor. But the fast PWM mode is recommended for applications like power supplies, voltage regulation, rectification, and digital to analog converters. And let's see how we can deal with that. Right. This is the timer value, right? So, and you have to write the timer value goes starting from 0 and goes to top. And this is your compare match value, right? What is the value that you have that you are going to written in that register TCROA? Okay, right. So the timer is counting from here to here, likewise, right? And so you are writing all CR0A register some kind of value, right? Let's say you have written the value to 50. So when the timer reaches this point 50, that there's a pin code for this to get this PWM output, OCA0 pin. This one, right? So that pin will be clear, which means its output will be set to low. And now the timer is still counting, right? It will count to 255 and reset to 0. In the CTC mode, we saw like the timer is reset, but here it is not. Timer is not resetting. Instead, it will just keep counting up to 255. Then it goes to 0, and it is counting up. When it meets this OCOA value, it will clear that, right? At the bottom, it will set. When it reaches to OCOA value, it will clear. Likewise, you can generate a PWM. So by changing this OCAO value between 0 to 255, your duty ratio can be adjusted. Like if it is a low value, so your turn on period is very low. You can see it's a very low. If it is somewhere here, the turn on period is a little bit high. If it is somewhere here, the turn on period will be something like that. You can take the invert waveform if so that is from the same pin you can take, but you have to write some values, set some bits, then you can take the inverted waveform as well. But most of the time, non-inverted waveform will be enough. So that's the operation. So like I mentioned, so you have to write the value to your OCOA register, and when it meets that register value, OCOA pin will be clear, and the timer is counting from 0 to 255. When it reaches the OCOA value, this pin will be cleared, and wait. In the next, when the timer reaches 255, that's the maximum value, it will restart from 0 and counting from here. And when it reaches that value, it will be cleared. That pin will be cleared. So that's the operation of fast PWM mode. So these are the registers that you have to work in the fast PWM mode. If you want to use the non-inverting mode, or CMOS A1 and CMO 0 of TCROA should be set to 1 and 0. This should be 1 and this should be 0. And waveform generating bits of 0A and 0B registers for fast PWM is this one is 1 and this one is 1 and this one is 0. You can see fast PWM. And the top value, typically we are using the maximum value of the timer, that is 255. You can also use OCRA value, but that is not used in most of the application. We are using this one. This is the compare value that you're using in OCR0A. So this problem is to generate 3.9 kilohertz PWM signal with 0.5 D2 cycle in fast PWM. So this kind of waveform. So this time period T is 1 upon 3.9 because the frequency is 3.9 kilohertz, 3.9 into 10 to the power 3 in seconds, right? And duty ratio is 0.5, which means like half of the time this will be on and half of the time this will be off. It's like a square wave waveform. Right. So this is how we're going to write this code. First, the main function, go to the setup. Setup here, we are using this pin, right? OCOA dedicated pin for timer output, compare output. So that is on port D. So I have to set the port D as output and initial set it to low. And I'm using non-inverting mode and top value is 255. So like I mentioned, so fast PWMA non-inverting mode. This is the non-inverting mode. If you're using the inverting mode, it will be this one. The waveform will be like that. But we are using the non-inverting mode. See. So non-inverting mode, this should be 1 and this should be 0, right? You can see CM0A1 will be high, this one. And so these two bits, fast PWMA, both should be set to high, right? So these two are set to high. And I'm using no prescale, so 1 microsecond update, which means I have to set this one to 1. So that is done in here. And I'm using, because the timer value can be 255 maximum, the half of that is around like 128. So OCOA value is 128, right? This one, this is 255. This is 0 and this is 255. And OCOA value I am using written in, it has 128, half of that one, right? So when it reaches there, it will be reset, and at the here it will be set and going down like that. Okay, so this is all about that fast PWMA. If you set this one and if you run that code and if you copy it to a microcontroller, it will generate that 0.5 duty cycle waveform at the output of this pin. This is the phase correct PWMA, so which is has a higher resolution than compared to the fast PWMA, which has a frequency of this is defined in this equation. This is a phase scalar. So the maximum frequency is half of the fast PWM. And in phase correct PWMA, so the timer value starting from 0 goes to 255 in typical scenario, right? And goes down to 0 and goes to 255. So this is how your timer value goes. And you can also write the OCR 0A value to any value. Let's say you write it to 128, half of that. So when it reaches, so at the top, this the output pin will be reset. Sorry, when it reaches from, let's say like this is the point, is starting from 0 and it counting up to 255. When it meets this OCRO value, the output pin will be reset, right? And it goes there and goes to 255 and coming back down counting, like decrementing the value. Again, you can see like it can meet this OCRO value, like somewhere here, right? So then it will set it. So clearing when it means when up counting, and setting when it means down counting. Okay, that's how it generates. You can see like the OCRO value is written here, 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 and here, right? So when it up counting, when it reaches that OCRO, it will be reset. When down counting, it will set. In up counting, it will reset. In down counting, it will set. So this is how you generate the phase correct PWM, which is suitable for motor controlling applications. These are the registers. So if you want to use these phase correct PWM, so you have to set non-inverting mode. So this bit should be 1 and this bit should be 0. At phase correct PWM, this waveform bit should be 0, 0, and this one should be 1. You can use any pre-scaler value. Now this is the last example. Here we have to write a PWM signal with variable duty ratio. So this is how I have done it. So I'm using that pin. So this on port D. So setting it to setting it as an output. Initial value is 0, and I'm using non-inverting mode, and top value is 255. So I'm using phase correct PWM. Top value is 255. This bit WGM 00 should be high. That's only one. 00 is high, as well as CMO 01 should be high, right? So that is all the values should be set to TCR0A, and I'm using no pre-scaler. Only this last bit should be set to high. So this is my main function, and I call the setup and do this setup and go to the while loop. And I'm using some kind of variable called duty ratio. So duty ratio is a for loop. Duty ratio is starting from 0, and it will count up to 255. And so each 10 milliseconds duty time period, OCRO value will be some value like starting from 0. And again, it is reducing that value. So which means like if you run this one, duty ratio is starting from 0 and like that. And every 10 milliseconds period, duty ratio will be increased, right? Likewise, the duty ratio will be increased. And after it reaches to 255, the maximum value, the duty ratio will be down counting. Right, so you can run this code and simulate, and you will see how it behaves, right? So this is a very simple example. There could be plenty of applications. So this is all about writing codes in Atmel Studio. And this is the end of the timers and counters.